lecture for our Emerging Technologies for the Circular Economy course. Today is going to be a two-part session. First, we'll talk about the Internet of Things in terms of communications as pitched last week. That's not going to be too long because we do not want you to become expert on different types of wireless communications, but rather make you or help you to understand, okay, there are different types of communication protocols that make sense for different scenarios, but you don't have to learn those by heart in terms of, okay, this is how bits and bytes are transferred here, and this is how bits and bytes are transferred there. We also don't want you to become an expert on the electric level for those protocols, so we'll keep this on a higher level. Afterwards, Anand is going to do the second part of this lecture on security and privacy. Similar goal there. We do not expect any of you, especially not the mining students, to become security and privacy experts for IoT applications, but we still want you to be aware of the fact that those issues have to be addressed. So that's going to be the two topics today. For the mining students, a quick note, and only for the mining students, not for the computer scientists and digital technology students. I think we have one more IoT lecture next week, and then afterwards we're going to split the course. Mining students go one track, computer science students go a different track. And for the mining students, we changed the course schedule. I think on the 6th of July, there's a different time for you to start the course, because Sana, who's going to take care of the two IoT mining specific lectures, has an invited lecturer who has just different time requirements. So please check StudIP, and I think also Sana sent you a message. So please keep that in mind, and only mining student specific content. That said, we have also another minor news or updates. It's time for the course evaluations. So this is the time of the year where we hand out QR codes and links. You don't have to do this right now. You can also do it after the lecture, and we'll also send at least one more reminder to please fill out the evaluation. As you can see, we have two different links for the different participants of our course. So mining students and emerging technology students. Would be nice if you can please separate your feedback. If you're a mining student, use one link. If you're a computer science student, use the other link, depending on which course you're actually taking. Please fill out the evaluation form and let us know what you think about this course. On one hand, we obviously love excellent and good feedback because that makes us very happy. But also let us know what we can do better, what you did not like in particular, and please also explain why. So for both things, like what did you like, so that we do not accidentally change those things you liked because we didn't know you liked them, but also for those where you're like, okay, this could be done somehow differently next time. So please don't just give us a bad rating without any explanation. We need to understand why. And otherwise we cannot really change something. We know that co-calc turned out to be a little bit difficult. We already know that. We're working on that, and we already make notes for the next semester on how to improve that. But if there's anything beyond co-calc that you either liked very much or did not like very much, please let us know. So that's also the news and update section. And now we're moving on to the actual content, or at least part number one of today's content, which is communications inside the Internet of Things. Last week, we closed with this overview figure that we've seen already a few times, but that we're also coming back to every now and then. Last week, we covered the left part of this figure. So we looked into some IoT devices like the Arduinos, the Raspberry Pis, and some other small computing devices, which either can do certain computations or just serve as a hub to host some sensors or actuators. We looked at different types of sensors. We also had a quick chat about some actuators, and that's where we closed last week. Today, it's about communications between those computing devices and sensors, but also when you're collecting sensor data on a larger scale, so many sensors placed on different places. How do they talk among each other, but also how do they communicate the collected data to some internet applications, some IoT platforms, some parts that we'll cover later, but how do they communicate? And there are, of course, like simple ways to just putting wires into everything, but those obviously don't work if you have placing sensors out on fields or in other remote areas like forests or whatever. And the different scenarios that we've briefly touched upon in the intro session, like having smart home automations where you have sensors in a fairly technological environment or in more remote environment, they obviously need different types of communication protocols or communication standards. Because out in the forest, you do not have Wi-Fi. At home, you more or less always have Wi-Fi. So there are just different approaches on how to enable communications among those devices. And today we're just going to look into some of those. One commonly used way to categorize those protocols that often helps to like separate them a little bit is to look at the different ranges for different types of standards of communication protocols. Usually there is some kind of a small range or small proximity set of protocols or communication standards that you can use that fall in this category of proximity. So there we're talking about RFID tags or NFC. One of the NFC applications that you may use on a regular basis are your payment via smartphones. So you have an NFC chip in your smartphone and your Visa card or credit card on your smartphone as well. You place it on the card reader and you can use it to pay. Those have a very, very, very limited range. Usually you do not want your Visa card or your credit card on your smartphone to be able to pay from 5 meters distance. Otherwise, people could just use that to scam you and take money out of your wallet without your consent. Usually you want to have the need for the smartphone to get really close to the payment terminal. So NFC and RFID are among those very close or small range networks that only work in very, very close proximity to each other. That's not too exciting, so we're not going to focus too much on those, but rather on the subsequent ranges and protocols. So first, there are so-called wireless personal area networks, WPAN. Then you have the wireless local area network, the Wi-Fi that you already know. We have the wireless neighborhood area networks, and then we have the wireless wide area networks. Personal area networks, usually something with 10 to 100 meters distance among the different devices. Wi-Fi works up to 100 and 1,000 meters. Neighbor area networks 5 to 10 kilometers, and then we have the long range up to 100 kilometers. First, already important point here is those are theoretical ranges that you can have maybe on an open field. As most of you have already experienced, usually your Wi-Fi does not work for 100 to 1,000 meters in your home. Some of you or most of you have probably already noticed that you might have a really good Wi-Fi connection in one of your rooms close to the access point, while you have a really bad Wi-Fi reception maybe in your, I don't know, bathroom, toilet, whatever, something that is rather far away from the access point. So those ranges are not cast in stone. They are dependent on different factors, like are there walls or some other barriers between you and the system who provides those networks. What type of barrier is it? Is it just like a small or a very thin paper wall, or is it 10-inch of reinforced concrete, or is it even a metal door in between? So those are theoretical values on with like any interruption, perfect line of sight, and so on and so forth. So please keep that in mind when we're talking about those ranges. First, we'll look into those wireless personal area networks. We'll look at Bluetooth, Zigbee, Thread, Z-Wave, and some of the other protocols. Then we'll have a quick look into the Wi-Fi-like protocols before going into neighborhood and wide area networks. So takeaway from this slide, different ranges for different types of protocol, which then also makes sense for different types of applications. Smart home like things would probably rather fall into this category here, while open field communication over large distances probably rather go into this direction here. So let's start with the personal area networks. And by the way, today we're only looking at the wireless stuff, because just putting a wire into something is not really worth discussing here, and is also for most IoT applications not really a feasible option, that you have maybe one sensor that just collects data somewhere and you put a wire into it. Sure, yeah, that works. But as soon as you have 5, 10, 20, 100 sensors, there are only very limited applications where you can still wire everything together. There might be in the industrial Internet of Things, so the IIoT, there might be applications for that, where you have large manufacturing sites where everything is wired anyway. But in those more ad hoc ways where you have like placing sensors for different purposes, there you're usually talking about wireless communication, because it's just way easier than placing wires everywhere. But that was just like a short side note. In the wireless personal area networks, we differentiate between so-called IP, so Internet Protocol-based systems, and not IP-based systems. IP is what most of you know from connecting your computer to the internet. You get a so-called IP address, which then identifies your device to, for example, a website. So when you're calling a website, you're sending your IP address with it, so that the server who's hosting a website knows where to send the website content back. So when you're streaming and asking for the latest Netflix show, this Netflix servers needs to know where it should send the video stream. So this is usually done via IP-based systems. And there are a lot of advantages to just hop onto the existing IP-based systems, because there's a lot of stuff already built into those protocols. But there can also be reasons why you do not want all of those extra features that you already get with IP-based systems. But this goes way too much in the electrotechnical direction and the theoretical computer science area than we would like to do. There are specific courses just on those types of things. We want you to understand the broader concepts and the high level stuff, so that you can decide, okay, this makes sense for my use cases or not. And of course, we're also not going to list all available protocols. We're looking at some of the more commonly used or protocols to understand like different applications here. So it's not a complete list, but it will give you an overview. So let's start with the IP-based systems. First, we look at the so-called 6LoWPAN, which stands for IPv6, so Internet Protocol version 6 over low power wireless personal area networks. It's a very specific protocol that uses the IP system, specifically the version 6, and relies on a low power approach so that you use as little power as possible for communication purposes. When you have your notebook plugged in or your smartphone or your desktop computer, power is usually not really a critical factor. But as we discussed in our last lecture, for wireless systems that potentially have to rely on battery powered systems or something similar, so something that is not connected to the grid, you have to care about your power consumption. Otherwise, you have to change your batteries every other day or every 6 hours. So the IPv6 over low power wireless personal area networks protocol is specifically tailored to use IPv6 in those personal area networks with as little power as possible. And low power means here something like less than 100 milliwatts. So 1 watt, like for example, a light bulb has something like an LED light bulb has something like 5 to 10 watts of energy consumption per hour. Milliwatt is a thousandth of a watt, so we're talking about something less than 100 milliwatts here. That is like one potential application piece. Then you also have certain types of Wi-Fi based systems. Usually they have these IEEE and then 802 something something something. Those are like a larger category of different Wi-Fi protocols. So also your Wi-Fi from home somehow falls into this broader sense of protocols here, even though this one is now specifically for vehicle-to-vehicle communication. Has a much higher energy consumption, which gives you more features. You can send higher data and so on and so forth. But also in a car, you usually do not really have a shortage of power. Whether it's a battery electric vehicle or an internal combustion engine car, usually the energy consumption of the infotainment system or the communication system is not really relevant compared to the energy that it takes to push a 1.5 ton car forward at 120 kilometers an hour. So that's why usually there you're not so keen or you're not so super pedantic on saving power in those scenarios. So it gives you a little bit of intuition what you can do there. Ruby is one of those very, I don't want to say niche protocols, but a very specific use case. It uses magnetic fields over short range. So a very, very specific thing. And is usually used in very harsh environments where you have to track something like high value assets. It has an extremely low power consumption, despite the fact that it gives you all the IP protocol features that are already quite comfortable when it comes to establishing communication between different devices. So just in those 3 examples of IP-based protocols for personal area networks, we have something from less than 10 milliwatts up to 1 watt. So there's a huge difference in terms of power consumption just for communication purposes. This does not include any of the things that your sensors are doing or any of the computation that are necessary for those sensors. This is just the communication. We also have so-called those not IP-based protocols that fall in this direction of personal area networks. Bluetooth is something that most of you are familiar with. Inside the Bluetooth protocol family, there are also different sub-protocols. On one hand, different versions of Bluetooth. So like the very early versions of Bluetooth are working slightly different despite being backwards compatible, or like the newer ones being backwards compatible to the earlier ones. But also within this Bluetooth protocol family are some protocols that are tailored and specifically designed to utilize as less or to use as little power as possible. So this is, for example, the case for BLE, which stands for Bluetooth Low Energy, so a very energy efficient version of Bluetooth. So it's quite versatile, has high data throughput per watt, but only works, as most of you know, from using, for example, Bluetooth headsets or other Bluetooth devices. And to a certain range, you usually cannot go that far with Bluetooth. Low power consumption is quite low. You're once again talking about something below 100 milliwatts, and you already have quite a lot of nice features built in that help you with drops of connections, data package loss when sending something. So similar to the IP protocol, you're getting already a lot of built-in things that you don't have to think about yourself. So what happens if a data package that you're sending is lost or corrupted? It's automatically sent again, or it's just handled properly. How do you know that the data package is complete or not? How can you check for a complete transmission? How do you know that someone actually received your packet? So there are a lot of things that you otherwise would need to build yourself if you're not relying on existing communication protocols. Zigbee is another low power protocol that is also similar to Z-Wave, very, very popular. So Bluetooth, Zigbee, and Z-Wave are probably among those that some of you or most of you are using in one way or another. I guess everyone somehow uses Bluetooth, either for headsets or for mouse or whatever. Zigbee, Z-Wave, probably everyone who has some kind of smart home thingies at home, whether it's a wireless speaker or I don't know, turning on your lights, smart LEDs or whatever, because Zigbee and Z-Wave are extremely popular in the smart home environment. So here we have Zigbee listed as mostly vehicle to vehicle. This is also true, but for example, I have a smart home thermostat by accident on my desk. This one is, for example, a Zigbee-based system. You can either tell it to automatically control or to set your temperatures, or what we are doing with those smart thermostats is when someone is opening the window at a certain place in the house, and automatically all thermostats nearby power off, so that you're not heating the room when the windows are open or when doors are open, because that would be wildly inefficient in terms of heating. So this is what Zigbee and Z-Wave are very good at. So very low power consumption. Z-Wave very similar. So both in those directions. IRDA, which is Infrared Data Association, is something that most of you might know from remote control. So you press a button and then you're sending like some kind of an infrared stream to a very pointed direction with some margin of error. And then you can do something like changing the TV program in the past. But nowadays I would say it became a niche protocol, but it still works and can be very efficient to communicate small information if you have a line of sight to your target. So now, for some of those protocols, a little bit of more pros and cons and fields of applications beyond what I just said. So Bluetooth, low power requirements, quite resilient against interference. So just here in this room, I have at least 3 Bluetooth-based systems. I have my keyboard with its Bluetooth connected. I have my mouse, my trackball Bluetooth connected. I'm currently talking to you via those Bluetooth headsets. My wife probably also has a Bluetooth headset on, so smartwatch as well, so 4. So you can operate quite a lot of those without getting into trouble, while still having all the luxurious pros of the Bluetooth protocol. On the contra side, you have a rather low bandwidth, so you cannot send large amounts of data through those things. So I can talk to you, I can hear you, but I cannot put a 4K video stream via Bluetooth. That would be really bad quality. It also has a limited range. If I now make my way to the kitchen with the headset on, I might be able to hear you near the fridge, but if I go to my microwave, I won't be able to hear you anymore because the Bluetooth connection is lost due to the thick walls that we have here. You also have a limited number of participants in a network. You can put quite a few Bluetooth devices into one network, but it doesn't scale up to hundreds of thousands of things. So where do you use it besides smart homes and your computers? Could be so-called Bluetooth beacons that you, for example, can use for localization services. Smartwatches, we already talked about this. Various non-critical medical applications also use Bluetooth, but obviously not those that are life or death applications, smart homes, smart cars, headset. So there are like different consumer products, great applications for Bluetooth systems or for Bluetooth-based systems. Zigbee, where I talked about the low power requirements, it scales much better than Bluetooth, so 6,500 nodes should work rather nicely. Once again, we have a rather low range, so I have 3 Zigbee repeaters in this rather large home to control these different thermostats and door things, but it works quite well. You also have a low bandwidth because they're usually built to just communicate rather small pieces of information, like what is the current temperature in the room, what is the setting of the valve for a certain thermostat. And then you can send commands like open the valve to heat the room or close the valve if you want to stop heating it, or you can send information like window open, window closed, but it's very limited in terms of what types of information you can send. There were also some security issues with some protocol design decisions in Zigbee, but it evolved into a quite major, not major, mature, sorry, mature protocol by now. If it would be still like it has some limitations in terms of security, but it is absolutely fine for quite a lot of applications like smart homes. But you wouldn't protect a bank vault with it. Where do I use it? Smart home. So obviously we talked about this. There are also some applications in the industrial sector where wired connections might not be suitable or not desirable. So yeah, it's a quite commonly used and very well-known protocol similar to Z-Wave. So back to our first IP-based one. So one of the pros is that it is IP-based and that you get all the nice features that the IP protocol provides you. One of those is, for example, built-in security, so that you have something like authentication of who sends me what, which you do not really have with Zigbee, for example. It also scales incredibly well because the IP protocol is essentially what our whole internet is based on or built up on. And you have literally billions of nodes operating in this network. So it scales quite nicely. Also, the fact that our internet is built upon it speaks for its interoperability. So if you have something like this protocol, you automatically are compatible with the largest chunk of the wireless communication and wired communication system that already exist. But it also has some minor disadvantages here. For example, a higher minimum requirements in terms of computational capacities or computational capacities, as well as hardware requirements in terms of, okay, what does my hardware need to be able to do? Because IP is a rather complex protocol. We're also listed not as popular as Zigbee or Z-Wave here, which sounds a little bit weird as a disadvantage on the first thought, but it is a disadvantage in terms of hardware available on the consumer market if you want to do something with it. So if I type in Zigbee thermostat into any search engine of your choice, you get hundreds of results. If you type in 6 slow WPAN thermostat, you're rather limited for the specific use case. So this protocol is used for very specific applications. Whether those fall into the category of consumer hardware is, usually not. It's just not as popular. It's essentially the point, but it has its use cases. whether it's being the wireless sensor networks or the Internet of Things, but mostly more in the direction of the industry, the industrial Internet of Things. Yeah, the IEEE. And in general, we talked about it, some kind of a Wi-Fi derivative that is quite popular in vehicle-to-vehicle communication, or when vehicles are talking to infrastructure like charging stations. It has some nice features that are relevant there, something like built-in time synchronization. For my thermostats, it's not really relevant that they are time synchronized. If you have two vehicles talking to each other, they should be very much aware of the shared time or the time stamp sharing that they have. So if you think about a scenario where two autonomous vehicles are driving next to each other, or where two vehicles are talking to each other, they should have the same timestamp. They need to know that for both of them, it's now 2:50 p.m. and I don't know, 25 seconds, and not like 30 seconds apart. Everything else might lead to critical situations. If you have a traffic light that thinks it's 5 minutes ahead in the future and tells you in 5 minutes that the LED will go green, your car will wait for 5 minutes while the traffic light is already back to red because it's 5 minutes ahead of you. So you need, for some applications, you need this time synchronization. So specific protocol for specific needs. Now we've covered the personal area network, the wireless personal area networks. Now we're going one step further, the so-called wide area networks. Most of you, if not all of you, I'm quite confident about that, have used either 2G, 3G, 4G, or are currently using 5G. Those are the most common protocols for your smartphones to connect, to be able to make calls, or to nowadays also use data roaming. So 2G is already quite old, 3G is what most of you have probably experienced, 4G and 5G is what most of you are probably using right now, so LTG or 5G. You have a historically increasing data throughput for those protocols, so 2G is quite old. There you couldn't even think about something like WhatsApp. Nowadays with 5G, it's no problem to even stream 4K streams on your smartphone because you just have enough bandwidth and can push a lot of data through this. You could also maybe think, okay, if I can do more, then the power consumption has probably went up. This is fortunately not the case because also the electrical hardware made quite a lot of progress, and the communication protocols in itself also got more efficient. So for 2G, we're talking about something like 1 to 2 watts of energy consumptions, while for 5G, we're having an average of 500 milliwatts to 2 watts, but it can also go beyond those 2 watts if you're talking about specific 5G hardware that pushes really a lot of data or has very strong sending devices, for example. So 2G, 3G, 4G, 5G, most of you have used it and have an idea what this is. There are also some more specific IoT related protocols, LoRaWAN, for example, and Sigfox. Those are systems very similar to 2G, 3G, 4G, and 5G. So they are also like those run via service providers that are placing base stations and radio towers across certain areas, which then provide you coverage. And you have to, similar to your 5G phone contract, you have to pay a monthly bill or something similar to be able to access this network. So this is what all of those wide area networks that we're talking about have in common. They need those radio towers and base stations, and they have some kind of a service or subscription model-based payment structure and also communication structure. But the difference here, if we're, for example, talking about LoRa now specifically, you can cover a much, much bigger area with a single LoRaWAN tower than you can do with 5G. So 5G, highly optimized for large data throughput, can cover small areas. LoRaWAN, as you can see, an extremely small data throughput, very, very small. Like, I mean, even here we're talking about megabits for 2G. Here we're talking about kilobits, so 0.3 to 50 kilobits per second. This is extremely small, but you have a tremendous coverage in terms of square kilometers here. That already indicates that you have very, very different use cases between 5G and LoRaWAN. So for example, we are using in our research so-called LoRaWAN sensors for the sensors on our research agricultural fields. So we have temperature and weather station data and soil moisture data sensors placed on a remote field. And yeah, there's quite a distance between the next LoRa gateway, which then is sending signals out and receiving signals from the sensors that cannot be matched by, for example, the Wi-Fi connection that we might have there. So it's a very, very easy protocol to set up, but you need some specialized hardware and you cannot put a lot of things through there. But it works, for example, for sensor data. And to compensate for all the downsides, so you have good coverage, you have very small power consumption, which is like on the plus side. On the downside is very low data throughput. So if you compare 5G and LoRaWAN, for example, you can see like 10 milliwatts as an average up to 100 milliwatts, and 5G starts at 5 times and goes up to 20 or 30 times that much. So yeah, you can see like the different use cases there. Sigfox, quite similar to LoRaWAN with comparable metrics, just a little bit less data throughput, but still similar use cases here. So cellular network architectures now in more detail. This is essentially 2G, 3G, 4G, and 5G. So you have a grid of cell towers. They overlap so that you can travel between different cells when you're talking on your phone, while driving a car, while being on a bus or on a train, or just walking through the city. There is an easy handover between those stations. It requires some network space planning. You have to divide those spaces into multiple accesses. You try to minimize interference, but still have enough overlap. So it's a little bit of a complex architecture to allow for large amount of network nodes, so users with smartphones, and also large data throughput. You need a quite dense systems of those towers, especially for 5Gs, like they have quite small cell structures to place all of them. So 5G being the most recent one. We're not going into too much detail here because in the IoT sense, it's not like this is more like for you to read up on later. But in terms of IoT, there are some applications where you have IoT devices communicating via 5G, but it's not that common. More common is this LoRaWAN, it's more common in the IoT sense, but it's also less commonly known for most of you. So we're going to spend a few minutes elaborating on this as well. While most or all of these 2G, 3G, 4G, 5G is in a so-called licensed spectrum. So people or companies have to pay the government a very large amount of money to be allowed to put out their base stations and radio towers to send out signals in those ranges and then provide services. This is not the case for LoRaWAN or LoRa itself, which uses a so-called unlicensed spectrum. So they're just using a different part or different wavelength that do not fall under this license agreements with the government. So that makes it already a little bit cheaper. But also they're using a wave spectrum that has waves that travel extremely far and thereby allows them to use a low number of base stations to cover wide areas. So, for example, 7 of those towers are enough to cover the whole country of Belgium. You wouldn't really get far with just 7 5G cell towers. with 7 5G towers. I'm not sure if I have a good comparison, but you would probably not even cover a decently sized village while still providing enough data throughput for all the inhabitants. So 7 for the whole country is quite good, but we already talked about the limited data throughput that LoRaWAN offers you. You also have a rather high latency. That means you will eventually get your data package, but it's not right away there. And it also misses some common features that you might know from 4G or 5G, but those are mostly relevant for those people on the computer science end. For example, you only have physical and MAC layers covered. Everything higher on the OSI layer system has to be implemented by yourself. But this is a rather specific side note for the computer scientists who are working on this kind of network topology. Then Sigfox, as I said, similar to LoRaWAN, it also uses part of the unlicensed spectrum uplink. So what they can send, 100 baud per second, is extremely low. It also has a payload limit, so you cannot send unlimited amounts per data package. It's just 12 bytes, which is extremely low. And you have a maximum of 6 messages per device an hour, which gives you roughly 130 messages per that you can send from any given device. Example, a sensor. So you can get a maximum of 140 readings per day from a certain device. You can try to get more readings, but then you somehow have to get them inside those 12 bytes, which then makes it once again a little bit more challenging. So for a lot of use cases, that is totally fine. How often do you measure the temperature outside? Usually 6 times per hour. It's totally fine. You don't have to measure temperature on a farm field every second or so. You're probably not gaining that much. Same maybe with soil moisture or other data points. For those use cases, it's absolutely fine to have these limitations. You probably won't notice them. The downlink, so what devices can receive via the Sigfox protocol, is 600 baud per second. You get an 8-byte payload and a maximum of 4 messages per day. So devices can receive 4 updates per day or 4 control commands per day. That makes limited use to use, for example, use Sigfox, for example, to tell it to open a gate whenever you're approaching your door or a certain location. Because if you have to visit it 5 times a day, suddenly it cannot receive the open command anymore. But if you, for example, I don't know, have an automated door system for your chicken coop, you can send it 1 command per day to open it and 1 command per day to close it. That's totally fine. So it depends a little bit on your use case. What's very nice about them, we have an open hardware system, so you can get a lot of open hardware there. But also the network is subscription based, so you have to pay a little bit of money there. So those were the wide area networks that have larger range than the personal area networks that we talked about before. So we had the very close proximity based systems like NFC or RFID. We had something that goes a little bit further like Zigbee or Bluetooth. And we also talked about this very large and long range systems like 2G, 3G, 4G, 5G, Sigfox and LoRa, to give you just some examples from every category with some application examples so that you get an idea, first of all, why do I need those different protocols, but also what are potential use cases for each of those protocols. That doesn't make you an expert on those protocols. There's a lot more to know about those protocols when it comes to making a decision which one to rely on for a complex IoT system that you might be task to implement, but at least it helps you to talk to people when those terms come up so that you understand, okay, we're using LoRaWAN, which means unlicensed spectrum, big network range in terms of coverage, but limited data throughput. That is already much more than you knew 20 minutes ago. And that you can compare it, for example, to 5G as a potential means of communication. That was one too far. A topic that is quite important when it comes to IoT platforms and designing the communication networks nowadays are so-called software-defined networks. Those apply on one hand in wireless networks, but also in wired networks. And you can do a whole lecture series, a whole course just on software-defined networks. And for the mining students, it might also not be super relevant. We will keep it extremely short. We just briefly wanted to touch up on this topic so that you are aware of this existence. The idea of software-defined networks is quite simple. You have, on one hand, in the real world, the actual physical network, which consists, for example, if we're talking about 5G, of cell towers that broadcast and receive data packages and then take it to the wired cable that it's connected to and then put it somewhere to data centers or the internet. And you have lots of those data towers. This is the physical system, the physical thing. So similar in your home, you also have physical hardware devices. So you might have your wireless access point, which is giving you Wi-Fi. That is connected via a cable to potentially your optic fiber router that receives the optic fiber cable from your network provider. So those are the real physical devices. In complex systems, it often makes sense to have so-called software-defined network that abstract physical layer and the actual virtual network layer from each other. So that you have a software layer on top that fully well knows what are all physical networking devices, but does not expose all of this to the software developers. So essentially you have this down here, physical network of many network switches. You have a so-called SDN controller, software-defined networking controller here, and all of the services and applications are just talking to this controller and saying, I need to send something to A, and whether the way to A is via this switch, and then this switch, and this switch, and then to A, in reality on the physical level, or if it goes this way, doesn't really matter to this virtual service, to this application. For your application, for your weather station dashboard at your smart home, it doesn't matter how you're getting there on a physical way, as long as you are getting there to receive or send data to A. And this is what so-called software-defined networks are doing. They are abstracting and hiding the actual physical way and providing you just a simple means of saying, send something to A, I don't care how it gets there. That sounds like an extra layer of complexity to most of you. I promise you, the more you're getting into this IoT platform space and designing IoT networks, and especially the IoT communication part, this makes a lot of sense. And it's also something that you very often have in data centers that manage large amounts of servers that communicate somehow with each other, or even network systems outside of data centers. So this makes a lot of sense to just have physical hardware that you can switch out, put something new in, and then it serves a different purpose. That makes a lot of sense. But we don't want to open up a whole new course on software-defined networking architectures. We just want you to be aware of its existence and roughly understanding this abstraction between physical existing network and a virtual network that just tells you how to get from A to B. So we have some nice features there, summed up by Anant here very nicely. It's a very flexible way to manage networks and optimize network resources, depending on, for example, how much the traffic load is there. The controller is generally a centralized simplifying implementation to control this logic. You have some complexity that you need to handle. You also need to think about security, scalability, and reliability a lot, but it is very nicely suited for a lot of cloud-based IoT systems that can make your life much, much easier. And that's all we're going to say on SDNs. We might, if we get the feedback that this is a really cool, interesting topic, going to do more on this in upcoming iterations of the course. But for now, for this semester, that's it when it comes to SDNs. Last small topic on for my part today are real quick look into so-called routers and gateways. Routers are usually the things that bridge two networks. So they are able to translate between different protocols. So for example, if you have optic fiber at your home, so having an optic fiber cable coming out of the wall from, let's say, the telecom, plug it into your router, and then it's able to translate whatever is coming in there to something out there in your home. It routes data, it has features like port forwarding, network address translation. You also sometimes have virtual networks. This is essentially what a router does. I have one network, another network in between a router, who's the communication party there. Gateways are bridges between wireless networks, or usually bridges between the wireless network and the internet. They can also translate between protocol, but you can think about it more like, for example, we have a LoRaWAN gateway on our test field. It has a Ethernet cable, like an internet cable, plugged into the device and uses that to then send out the LoRaWAN signal to the LoRaWAN sensors on our field. So that is what a gateway does. It provides the entry point to a network. Make it a little bit more confusing. Routers can be gateways, but don't have to be gateways. So for the sake of having a proper communication about different networks, protocol and communication protocols, we just wanted to clarify what is a router and what is a gateway. Very simple. And we'll get back to some use for gateways in the context of edge and fog computing in lecture 8, which is next week on IoT data processing and big data. We'll have another example for gateways. We also have, and the IoT mining students will have a chance to play around with them, some gateway examples in our lab. So for example, wireless sensor nodes running the so-called contigi, which is for IPv6. The node attached to a gateway over, or nodes are attached to a gateway over USB. They act as a gateway, so chip to chip. And it provides the IPv6 connectivity between network providers through so-called serious line internet protocols. Don't learn this by heart, it's just an example. We have those gateways in the lab and you can play with it if necessary. So that was my part for now. Evaluation, please let us know what you think about the course. That was the first thing. Second, we talked about IoT communications protocol on a very high level with a certain selection of relevant protocols for different network ranges or coverages. So proximity, close by personal area networks and very large ranging networks, and looked into like some different aspects there. We briefly touched up on the software defined networking and what use case it has, and we also briefly clarified, okay, what's a router, what's a gateway. And that said, I'm done for today.